Hey everyone, welcome back to the next video in the course. In the last episode, we set up the foundation of our hearing system. And in this lesson, we're going to continue with that and develop our sound stimulus scoring system. Please be sure to like the video and subscribe to the channel. As usual, the project files for this course are available to download completely for free. If you would like to show some support, please be sure to donate either via the Gumroad link or via the Buy Me a Coffee link in the video description below. So let's get into it. So I'm going to take you on a quick tour of what we'll be constructing in this lesson. We've already set up the foundation of what we need, and we're going to focus entirely on this function here, the get highest scoring stimulus. Now this function contains within it functions within functions. So there's actually quite a lot we're going to be making in this particular episode. So let's take a quick look at what we'll be making. So right off the bat, the main scoring function is actually this function here, the get score for sound stimulus. And we run this function on each stimulus that we pass through. And whichever stimulus gets the highest score will win against the other stimulus. You might also notice this additional function here, which I will get into later in the video. This is a very versatile function which gets all of the values for our scoring system. And this function itself utilizes a custom data table that I've constructed where we can input our values for our scoring system. We're going to be learning quite a bit more about data tables in this lesson, actually. This won't be the only time we'll be using it. And data tables are very useful for this use case where we need to retrieve certain predefined values for a lot of different use cases. Anyway, let's go back and let's take a look inside the get score for sound stimulus function. Now, this is where everything happens. Initially, we enter this function and we are setting some local variables that will only be used inside this function. And then we have a sequence of logic in our first row here. We are calculating some raw score values. So the first one we're going to be calculating is our priority score. Now, our priority score will be determined based on the tag. If you recall from the last lesson, we discussed the report noise event function. This is how we report a noise event from the environment. And in it, we can place a tag for that particular noise. So for example, a gunshot, a footstep, and so forth. But what we'll be doing is we'll be taking that tag and we'll be converting it into a gameplay tag using a special function, and again, using data tables to process that conversion. So if we go inside this convert to gameplay tag, we'll be feeding in the tag from the noise event, comparing that tag against the row name of another custom data table, and then outputting the converted gameplay tag for that particular row. So for example, if we have an incoming tag called gunshot, we can output a gameplay tag that we specify, and then from that gameplay tag, we can determine the priority that should be given to that noise event. So a high priority score of 1, medium of 0.6, and a low priority score of 0.3. And we have a default of 0.3 for any noise events either don't report a tag or don't have a matching gameplay tag. And then from there, we set the raw priority score. Next, we calculate the raw recency score. So the more recent the sound, the higher the score. Now, what we basically take in here is we basically feed in a game time, which is the equivalent of the current game time minus the time that the noise event was heard. And we feed in that value, and then we map that value to a range based on a sense decay threshold and a sense decay floor. Now, this may not make too much sense just yet, but we'll be going much further in depth when we actually get to this. But from this, we output a raw recency score between 0 and 1. Next, we calculate the raw distance score. Now, this is a fairly simple implementation of a distance score. It's simply based on how close the sound is to the alien in the physical environment. Now, I have left a note here that the closer the noise, the higher the score, but this could be refined further by conducting an EQS query to obtain the cost of the navigation path. So in other words, a shorter distance in the world doesn't necessarily mean that it's the shortest navigation path. So you might have a very close world distance, but they might be on the other side of a wall, and the alien might have to travel quite a distance to be able to get to that noise event. So for now, calculating a simple real world distance is fine. And when we eventually get to learning environmental query system, we will update this to reflect a more robust score for the distance. Now, moving on, after we've calculated the raw scores, we then calculate a weighted score. Now, what we're doing with weighting is that we're assigning a weight based on what we believe is more important. So, for example, if we have a priority score of, let's say, 0.6, we can take that raw priority score of 0.6 and multiply it by a weight which we assign to how important priority is to calculating our final score. So if we go back to the data table I showed you just a minute ago, I've assigned a weight to recency, distance, and priority, and I've given the highest weight to how recent the sound was in the environment. So the recency weight will be 0.5, the distance weight will be 0.3, and the priority weight will be 0.2, and all up that equals a value of 1. And that's just to split how important we define these three variables. So we're assigning a greater importance to how recent the sound was in the environment than we are to how far away the sound was, or the level of priority that our tag assigns. So just coming back to our scoring system, so we calculate the weighted priority score, then the weighted recency score, and then the weighted distance score. And once we have those weighted scores, we finally add in a final multiplier based on whether or not the alien has already investigated the sound that we're scoring. So if the agent has already investigated the stimulus, apply the has investigated multiplier to reduce the score. So if we have two sound stimuli that the alien is trying to score against, and the alien has already investigated one of those sounds, and it hears a new sound that it hasn't investigated, we want to give a much higher priority to that new sound that it hasn't investigated. So for any sound that it has already investigated, we multiply that by a value of 0.1. So let's say, for example, we have a weighted score of, let's say, 0.8, but the alien has already investigated that sound. So then we apply the multiplier of 0.1. That would lower the score drastically. And then from all this, we get our final score, which will be output from the function. After that, I've just added a print debug function here, which is a development only function. I'll show you how to set a function as development only a bit later in this video as well. But essentially, we're feeding in all this information and then printing the score to both our screen and our log, so that we can investigate how our sound event is being scored and what the final output was. And then finally, at the end here, we output our final score. So that's basically what we'll be building today. There's quite a lot to cover, so let's get into it. Okay, so I'm here in the run sound stimulus decision tree function that we set up in the last video. I'm going to go inside the get highest scoring stimulus function. Now, at the moment, this has no logic inside it. We're going to go ahead and enter in some logic now. And the first thing that we're going to do is we're going to create the pure function for getting the score for the sound stimulus that has been fed in through this input. So we'll go up to functions and add a new function, and we'll call this get score for sound stimulus. And this will be a pure function, and we'll set the category to handle stimuli and the subcategory sound stimuli. This function will have two inputs. First input will be type f cached stimulus, and we'll call this stimulus. And the second input will be of type Boolean, and we'll call this is primary. We'll also have one output parameter, and that will be of type float, and we'll call this stimulus score. I'll just go back up a level, and in our function here, we will drag in our new get score for sound stimulus, and we'll drag in another one as well. And we'll hook up the A primary to stimulus. And because this is the primary stimulus, we will check the primary Boolean. And we'll also hook up our B stimulus. And because this is not primary, we'll leave primary unchecked. And we just need to determine which is the highest scoring stimulus here. So we can simply drag off and do a greater than and hook that up like so. We will be adding an additional function in here later, but we'll come back to that. For now, let's just go back inside our get score for sound stimulus, and I'll break this execution. Now, the first thing that we need to do is we need to set a number of local variables that will be used inside this function. So let's grab our stimulus and break the struct. We'll come back to the received stimulus info struct in a moment. For now, I will promote our stimulus ID to a local variable. Just call it stimulus ID. You'll notice the little V icon here, which just signifies that this is a local variable that does not exist outside this function. Next, we'll promote the has investigated to a local variable. And you'll also notice that local variables will show up in this section down here for local variables, not in the variables for the class. And for now, we don't actually need to reference the is valid Boolean. So we'll just come back up to the received stimulus info. And I'm actually going to split this. So I'll right click the pin and click split struct pin. And the one we need access to is the received stimulus struct inside it. So I'll go ahead and break that. And out of here, we need the stimulus location. So I'll promote that to a local variable. Call that stimulus location. And we also need the tag promoted to a local variable as well. Call that tag. And finally, if we come back to this section here, we also need the time received. So I will promote this to a local variable as well. And I'll call this game time received. Great. So that's all the local variables we need to set for now. Next, we'll be running a sequence node. So we'll drag off and type in sequence. And for our 0 pin, we will be calculating all the raw scores. And first up, we will be calculating the raw priority score. So we need to set up a couple things in order to get that score. But if we check my demonstration project, we first get our tag and then use a custom function to get the stimulus priority. And then we set the priority score based on what that tag information provides us. So we'll need to create a new pure function called get stimulus priority. Let's create a new function now called get stimulus priority. This will be a pure function, and we'll assign this the category of handle stimuli. This will have one input, and this will be of type name, and we'll call that input tag, and it will have one output, and this will be a new enum value. So we'll need to create a new enum. So we'll go to our content drawer and then go to our enums folder, right click, blueprint, enumeration, and we'll call this enum underscore tag priority. Go ahead and open that up. And we need to set 4 priority levels. So we'll add 4 enumerators. Our first one we'll call high. Next will be medium. Third will be low. And our final enumerator will just be called default. Save that and go back to our function. And now when we click on our return node, under the output type, we will type in enum underscore tag, and we'll assign tag priority. And we'll call the output stimulus priority. But we're not done yet, because now we need to convert the tag that we receive from our noise event into a gameplay tag. So I'm going to create a new function again. This will be called convert to gameplay tag. Again, this will be a pure function, and we'll leave the category as default. That's fine. We'll create an input. This will be of type name, and we'll call this tag. And we'll add 2 outputs. First output will be of type Boolean, and we'll call this is valid tag. And the second output will be of type gameplay tag, and we'll just call that gameplay tag. So we've got two new pure functions now that we need to build out. We'll build out the convert to gameplay tag function first, because our get stimulus priority function will depend on that. So now what we need to do is we need to create a data table for our gameplay tags, but this is not going to be the same kind of data table that we had been creating for our other gameplay tags. So if we take a look at one of these data tables that we've already created, for example, let's have a look at DT alien motivation. You'll see up here that the row type is called gameplay tag table row. This is a data table that comes with Unreal. And now it's important to explain what exactly a data table is and how we can create custom data tables. Data tables essentially derive from structures. All data tables will have a column called row name. The struct that the data table derives from will determine how many columns there are and what types those columns are assigned. So this data table is derived from a struct that has two variables. So we have the tag and the dev comment. And if we hover our mouse over the column heading here, you'll see that it'll tell you what type this variable is. And this says it's a name property. So this variable is of type name. And if we hover over dev comment, it's a str property. So it's a string. So this data table derives from a structure that contains a name variable and a string variable. So if we wanted to create our own custom data tables, what we would first do is create the structure that that data table would derive from. So if we go to our content drawer and go up to our alien folder, we already have a structs folder. So we'll double click on that and we'll right click in that folder and go to blueprint and then structure. And we'll call this f_tag lookup, and we'll double click that. Now for this structure, I want to have two variables as well. The first variable will be of type gameplay tag. So we'll select gameplay tag and we'll call this tag, and we'll add a new variable, and this will be of type string, and we'll call this variable developer comments. And we'll go ahead and save that. So now what we can do is we can create a data table that derives from this structure. So let's go to our content drawer again. We'll go to our data tables folder and we'll create a miscellaneous and then data table. And now for pick row structure, all we have to do is search for this structure we just created, and it's f_tag lookup, and we select OK. And now we've got a new data table. We'll call this DT_alien_heard sounds, and we'll go ahead and open that up. And now we have a data table, which of course has the row name column, which every data table has. And we have our tag column and our developer comments column. If we add a table row, you'll see that in our table row here, we can select a gameplay tag, and we can also add in a comment. So that's how you can create a custom data table. It's really straightforward, and these are super useful. So let's go ahead and add in our different tags. So what we're going to do here is we're going to define the row name using the same name that we would use for the tag that we report in our report noise event. So just for demonstration purposes, I'm just going to go up to where we were reporting our noise event. I believe it was in the player character class. Let's have a look. Or it might have been in our player controller class, actually. Let me double check. So under core, player controller. Yes, here we are, report noise event using the debug key ends in our alien player controller class. So when we report a noise in the environment, we can, for example, type footstep so that we can let our hearing system know that we've reported a footstep, and then we can then use that information to derive the priority of this noise event. I'm just going to delete that for now. So let's go back to our data table. I'm going to define the row name based on what tag we will put into each noise event. So to rename the row name, you can select the row and press the F2 key. And I'm going to call the first one gunshot. Now we need to create some more gameplay tags. So let's create a few gameplay tags for different types of sound events. So I'm going to go back to our content drawer, and we'll go to the data tables folder, right click, miscellaneous data table. We'll select the gameplay tag table row. Okay. Call this DT_alien_ heard sound tags. Open that up. And let's go ahead and create 3 different tags. So I'll create 3 new rows. The first row, let's call this alien dot reception dot here dot, and then what we're going to do here is we're going to define the priority of the actual sound. So we'll start with high, and then dot, and then the type of sound that's being broadcast. So we'll do, for this one, gunshot. So this is how we'll derive the priority from the gameplay tag. And this is the reason why we're converting the sound event tag into a gameplay tag, because we can use gameplay tags to derive the priority of that noise event. So we can create a number of different gameplay tags that derive from the high priority, medium priority, low priority, etc., etc. So let's create a medium priority sound. This will be footsteps. So alien dot reception dot here dot medium dot footstep. And let's create a low priority one as well. So we'll do alien dot reception dot here dot low dot, and let's just create a general environmental noise. So we'll do ENV for environmental. So this will be, for instance, if perhaps a character or an NPC knocks something over in the environment, and that's an unknown environmental noise, that will be a low priority. Let's go ahead and save that, and we'll go back to our heard sounds data table. And let's add in our first tag for the gunshot. So this will be alien perception, here, high priority, and then gunshot. And in developer comments, just because it's not as easy to read from the tag here, let's just use the developer comments to define the priority. So we could call this high priority. Okay, let's add in another table row. We'll rename this row to footstep. And the tag, so we'll do alien perception here, medium, and then footstep. And I'll just write a comment, medium priority. You can leave whatever comment you like. This is just for your own reference. We're not actually going to be utilizing developer comments in Blueprint, so that's fine. Next, we'll create another row, and we'll call this environmental. We'll select alien perception here, low priority environmental, and then just call this low priority. And save. So now we've got 3 different noise events, each with their own level of priority, which we can derive in blueprints. Now, I almost forgot, but now that we've created a new data table that derives from the gameplay tags structure, we need to add this gameplay tag data table to our project settings. So we'll go to Edit, Project Settings, and then under Gameplay Tags, Gameplay Tag Table List, we'll add a new array element and select our new heard sounds tags data table, and just close that. Great, so now we've got 3 rows in our new data table. But how do we retrieve this information at runtime using blueprints? So let's go back to our function that we created, the convert to gameplay tag function. Now, when we receive the tag input, what we're going to do is we're going to right click and type in get data table row. And we want this one here under utilities. We'll hook that up. Now we have to define the data table we're searching for. So it's the alien heard sounds data table. And what we're looking for is a match to the row name. So our tag is of type name. So if the tag matches the name of the row in the data table, it will output the gameplay tag from that row. So we do need to make sure that the spelling is correct in our row name so that it equals to the name that is reported by the tag in the report noise event. So if we have successfully found the row, we will hook up to the return function and the isValid tag will be true. And to get the gameplay tag, we actually need to right click this struct and split struct pin. And that gives us access to the out row tag, and we can hook that up to gameplay tag like so. However, if we don't find a row with a matching name, we'll return out of the function as well, but this time we'll leave isValid tag unchecked because we weren't able to find a valid tag. So this function is now done. We can return to our getStimulusPriority function and drag in our convert to gameplay tag. So if we hook up tag to the input of that function like so, and if isValid tag is true, we'll add a branch. If isValid tag is false, we'll just add a print string and type in no valid tag found. And then in brackets, I'll just write the name of this function. So if it prints to the screen, we know where it's coming from. So I'll just write get stimulus priority. Next, after we've checked if the tag is valid, we want to check if the tag matches one of our 3 priorities. So out of gameplay tag, we will drag off and type in matches tag. And we'll first check to see if it's a high priority. So we'll go alien perception here and high priority. We will leave exact match unchecked. And then we'll add in a branch and hook that up like so. If it is a match for high priority, we will return out of the node and leave stimulus priority assigned to high. If that's not a match, we will then check to see if it matches the medium priority. So we'll drag off and type in matches tag. We'll select alien perception here, medium, add in a new branch and hook that up on the false pin. If we do have a true match for a medium priority, we will return out of the function and assign our output to medium. Finally, if it doesn't match either high or medium, we want to check if it matches the low. So we'll type in matches tag, select alien perception here, low, add in a branch. If it is a match for low, we will return out of the function and assign our output the value of low. And if none of those are a match, that means likely we didn't find a valid tag. So we will simply return out of the function and assign the value of default. Hey, future student here, just coming back to fix a small mistake I made. So everything we've done so far is correct, but the only thing that we need to make sure that we do here is out of this print string node, we want to connect this back up to the branch here. Because if we don't do this, then if the tag is not valid, then it's simply going to exit out of the function and it won't proceed to assigning a default value for invalid tags. So we just need to make sure that we do that, and this function is now complete. Back to the main video. Great. So if we go back up to our get score for sound stimulus function, off the 0 pin on the sequence, we will add our local tag variable as a get node. We will use our new getStimulusPriority function and hook that up like so, which will return the enum value of our stimulus priority. Then what we'll do is we need to create a new local variable called our raw priority score. So we'll create a new local variable called it raw priority score, and this will be of type float. We'll drag that on as a set node. And then out of the input for this, we'll type in select, and we want to select the one under utilities. And then in our index wildcard here, we'll add the stimulus priority. And this will allow us to define what the priority score is for our high, medium, low priority noises, as well as the default. So for high, I'm going to assign a score of 1. For medium, I'll assign a score of 0.6. For low, I'll assign a score of 0.3. And we'll have the same score of 0.3 for anything that returns an invalid priority. And we'll hook up like so. Just highlight this and add a comment. Calculate raw priority score. Okay, now that we've retrieved our raw priority score, next thing we're going to get is calculating our raw recency score. And if we go back to the demo project I made earlier, we'll need to create that special function I mentioned earlier in order to retrieve some values for us. Now, if I just quickly go into this function, what we're essentially doing here is we're getting information from a data table similar to what we were just retrieving with the gameplay tags. So we're going to be creating a new data table again. And the data table we're going to be creating is our perception scoring values. So this is a convenient way to list out a number of scoring values for different things that we're trying to retrieve. So let's go ahead and do that now. So in order to do that, we need to create a new structure to base our data table off. So I'm going to go to our content drawer again and into our structs folder, and I'm going to create a new struct. So under blueprint and structure, and we'll call this F underscore perception scoring. And we'll open up that struct. And for this structure, we'll have two values. The first variable will be of type string, and we'll call that variable type. And the second variable will be of type float, and we'll call that return value. So now we'll go back to our data tables folder, and we'll create a new data table. So right click miscellaneous data table, and we'll select the structure we just created, F underscore perception scoring. Okay. And we'll call this DT underscore perception scoring. And open that up. So now we've got our data table with the two variables from our structure, and of course the row name column, which is common for every data table. I'm going to go ahead and create 7 rows here. So I'll create 1, 2, 3, 4, 5, 6, 7. Select the first row, press the F2 key to rename. And the first one will name recency weight. For type, this is just going to be a simple string value. I'm going to call this scoring weight. And I'm going to give recency a weight of 0.5. We'll select our next row, press the F2 key to rename, and I'll call this distance weight. Again, for our type, I'll just copy and paste what we've put in our first variable, in our first row, scoring weight, and the weight I'll give distance is 0.3. Next, name priority weight. Again, this will be type scoring weight, and I'll give that a value of 0.2. So all up, these three values equal a total weight of 1. So 0.5 plus 0.3 plus 0.2 equals 1. Now, the next two rows that we're going to create are going to be related to how we calculate our recency score. So just coming back to my example project in a minute, I'll explain how this is actually working. So what we've got here is we're first getting the current game time and subtracting the game time heard from that to output the game time in seconds since this noise was heard. So let's say that we output a value of 35 seconds. So in that case, it's been 35 seconds since this noise event has been heard in the environment. So what we're doing with that is we're taking that 30 seconds and we're essentially mapping it to a value between 0 and 1. What we're doing is we're mapping that value of 35 seconds against a range that we're defining. And the range we're defining is the range between the sense decay floor and the sense decay threshold. So basically, let's say that we set our sense decay floor at 0.1 seconds. So that's extremely recent. And then our sense decay threshold, let's say that that's a value of 90 seconds. So that means that the noise would have been heard a minute and a half ago. So let's say that we had a noise in the environment that was heard 90 seconds ago or longer. Because that 90 seconds reaches the threshold that we define, that means that that score is effectively 0. So if we get a sound in the environment that was heard 90 seconds ago or longer, then the score will be 0. The noise was, let's say, 0.1 seconds ago, which would be our sense decay floor, then that would be given a score of 1. And any value in between these values of 0.1 seconds and 90 seconds will be mapped in between the score of 0 and the score of 1, depending on how close they are to those extremes. I hope that makes sense, but that's essentially how the map range clamped works. So just coming back to our data table, if we select row 4 and press F2 to rename, we'll call this row the sense decay threshold. And under type, we'll call this type a limit. And we'll set our return value at 90 for 90 seconds. Next row we'll select will be row 5, and we'll call that sense decay floor. Again, the type will be limit, and this time our return value will be 0.1. So this is essentially the range of time we're mapping our recency score to. And now row 6, we'll select row 6, press F2, and we'll call this has investigated multiplier. For type, I'll just call this a type of multiplier, and we'll give that a value of 0.1. So as I mentioned earlier, if the alien has investigated this particular noise event, then we will multiply the score by 0.1 to drastically reduce the score of that noise event. And then finally, row 7, it's going to be an interesting name. So press F2. This is called hysteresis, and it's spelled Hysteresis. This is going to be of type bonus score. I'll type that in here. So bonus score under type. And we'll give that a score of 0.02. Now you can think of hysteresis as a kind of momentum in the alien's decision making. So if I bring you back to the example project just for a moment to show you how we're going to be applying this. In the get higher scoring stimulus function, what we're doing here is for our primary stimulus, we're giving a bit of a bump to the score of our primary sound stimulus. So our primary sound stimulus score is going to get us a bump of 0.2 points to its score. Now, the point of this is that if we read this comment here, hysteresis bonus is applied to the primary sound stimulus score, meaning that any new competing sound stimulus has to score meaningfully higher in order for the agent to change focus on the object it has committed to. So when I say that you can think of hysteresis as a kind of momentum in the alien's decision making, basically what this means is that because we have a primary sound, we're assuming that the alien has already committed its decision making to investigate this primary sound, and any competing sound stimulus would have to score meaningfully higher than the primary score in order for the alien to change its decision. So we do that by adding a slight bump to the score of our primary stimulus. And this also means that scores that are really close together won't oscillate back and forth between the primary and competing sound stimulus, because any new stimulus receives has to score meaningfully higher than the current stimulus that the alien has committed to. So that's basically what that is. So we'll go back to our data table. And now that we have this data table ready, we can go ahead and create that special function that I mentioned earlier. So we'll go back to our evaluator and we'll create a new function, and this will be called get perception scoring value. Again, this will be a pure function and it will be in the category handle stimuli. Now what we're going to do is we're going to set the input of this function as an enum that we can select from a drop-down, just to make it easier to retrieve the value that we're searching for. So for that, we'll need to create a new enumerator. So we'll go to our enums folder, create a new enum. So blueprint enumeration, call this enum underscore perception scoring. We'll go ahead and open that up. Now what we're going to do here is we're going to create an enumerator for each of the rows in our data table, but the thing we have to be mindful of is that we have to use the exact spelling as what we've specified in the row name, because that's how we're going to be retrieving the value from this data table. So I'm going to create 7 enumerators, 3, 4, 5, 6, 7. And I'm just going to copy the text so I don't get any spelling mistakes. So I'll press F2 and then Control C and then Control V into our first enumerator. And I shall do this for each row. Once that's done, we'll save it. We'll go back to our new function, select the input node and add a new input. And this will be of type enum underscore perception scoring. And we'll call that row name and then compile. So now that we've added that enumerator as an input, if we were to add this to our event graph, we can now select from a drop-down menu the value that we're trying to retrieve. So I'll just delete that for now and go back. So now we need to get the data table row. So we'll right click and type in get data table row. And you want to make sure you want to get this one under the utilities heading. These other two ones won't work the way we intended to. So we'll just make sure you grab that one and we'll hook up the execution. Now you might think that if we just hook up the row name to the row name, this little converter will convert the name of our enumerator into the row name text, but this won't actually do what we want it to. What we have to do instead is out of row name, we type in enum to string and select that. And that function will convert the exact name of our enumerator into a string. And then we can add the string into our name variable, and that will add a string to name converter. And of course, we actually need to select our data table asset. So we'll select that, and it is DT underscore perception scoring. We can right click our struct and split the struct pin to retrieve the return value. So we actually need a return node. So out of row found, I will type in return. And with the return node selected, I will add an output, and this will be of type float, and we'll call this float return value. Also, I'll add another output of type Boolean and call this is valid row. If we have found a row with a matching name to our enumerator, then is valid row will be checked true, and we will return the float output here into the return value of the return node. Otherwise, if we don't find a valid row name, I will drag off there and add a print string and just write no valid row found, and then in brackets I'll write the name of this function so that we know where it's coming from. Get perception scoring value. And then out of that execution, we'll add a return node again. The return value will be 0 and is valid row will be left false. And that's how we can retrieve each of these values that we've put into our data table using blueprints. Again, the thing that you just need to be mindful of is that you first need to make sure that each of the enumerators are exactly the same spelt names as the row names in the data table. So that means if you happen to change one of the names of the rows in your data table, you also need to make sure that you update the name in your enumerator as well. That's all we need to do for this function. So we can go back to our get score for sound stimulus function, and then after the raw priority score is calculated, we'll calculate our raw recency score. So we need a new local variable. I'll add a new local variable and call this raw recency score, and that will be of type float. I'll drag this onto the graph and hold down the Alt key and then release the mouse button to automatically add a set node. By the way, if you want to automatically add a get node, you can do the same thing, but holding down the Control key instead. just a little tip to make things easier. So we'll hook up the execution to this node here. And to calculate the raw recency score, we need to get how many seconds has passed since the noise event occurred. So to do that, we will get game time in seconds, and then we will subtract our local variable called game time received. And then that will give us how many seconds have passed since this noise has occurred. And then out of that return node, we'll add the map range clamped. We want the normalized range of this output to be between 0 and 1. So in range A will be 0 and out range A will be 1. Now, in order to actually get the value, we need to map the incoming value against that 0 to 1 range. So to map it, we need to tell this node what the extremes are. So in range B, we'll use our new function that we created, the get perception scoring value. And we want to retrieve our sense decay threshold. And we'll add the return value from that into in range B. So if you remember, our sense decay threshold was set at 90 seconds. So any noise that occurs up to 90 seconds or longer will be mapped to the score of 0. Now, our other extreme will be our sense decay floor. So we will get another one of those functions and we will select sense decay floor and hook our return value up to out range B. And then finally, that return value will set our raw recency score. Go ahead and highlight all this, press C for comments, and I calculate raw recency score. And in brackets, the more recent the sound, the higher the score. Great, we've almost finished our raw scores. The last raw score we need to calculate is our raw distance score. So I'll go ahead and create a new local variable, and this will be raw distance score. Again, of type float. Drag that onto the graph, hold Alt and release to add the set node, hook that up. Now what we need to do here is we first need to calculate the distance between our stimulus location, or the location of the noise, to the alien character itself. So we've already got our local variable of stimulus location. I'll drag that onto the graph, hold Control and release. And then we'll use the distance vector node. So I'll drag that off and type distance and then select distance vector. This returns the distance between two vectors. And to get the second vector, or in other words, the location of the alien character, we'll use our context reference for our alien character as a get node, and then get actor location and hook that up to the input. So the return value, that will get the distance between our stimulus location and the alien character. Now we need to use our map range clamped function again. So we'll drag off the return node and type map range clamped. Our normalized score, we want to be between 0 and 1. So in range A will be 0 and out range A will be 1. In range B will be our max hearing range. So to get that, we need to use a special function from the Metaxas AI Perception Tools plugin. So make sure that's installed. Otherwise, you'll need to enter the max hearing range manually in this field here. But I'm going to drag off the Alien AI controller ref. And then from there, we need to get AI Perception Primary, which is the name we gave to our primary AI perception component. And then from there, we get the Metaxas AI Perception Tools function, which is get hearing range. And we hook that up to in range B. So just covering what we're doing here again. So the normalized value we want to calculate is a value between 0 and 1. and we map that range onto the max hearing range, which maps to the score of 0. So the further away the noise is, the closer to the score of 0 it becomes. And the score of 1 is mapped to the closest range of 0. So the closer the noise is to the alien, the closer the score gets to 1. I hope that makes sense. So we'll take our return value and add it to our raw distance score. I'll just comment this out here. Calculate raw distance score. And then in brackets, the closer the noise, the higher the score. Great. So now we've got our 3 raw scores calculated. Now we need to calculate our weighted scores. Now this is actually really easy. So out of pin 1 of our sequence, we will set our weighted priority score. So we need to set a new local variable, and this will be called weighted priority score of type float. Drag this onto the graph, hold down Alt and release, and we'll hook this up to our pin 1 on the sequence node. Now the way that we calculate our weighted priority score is really easy. All we have to do is we get our raw priority score that we calculated up here, and we multiply that. And if we get our get perception scoring value function, and then we'll select our priority weight, and we multiply the raw priority score with our priority weight. And then you'll remember that the priority weight was a value of 0.2. And then we use that return to set the weighted priority score, and that's it. You can go ahead and comment out this. Calculate weighted priority score. Now we calculate the weighted recency score, which is basically exactly the same. We'll create a new local variable again and call this weighted recency score. Drag that on as a set node. We'll get our raw recency score and multiply that by our recency weight. Then hook that up to the return value. Calculate weighted recency score. And then finally, we need to calculate the weighted distance score. So again, we'll create a new local variable, call that weighted distance score. Drag that on as a set node. We'll get our raw distance score and multiply that by our distance weight. Comment that out. Calculate weighted distance score. Great. So now we've calculated our raw scores for priority, recency, and distance. And then from those values, we calculate our weighted scores for priority, recency, and distance. And now we need to calculate our final score. And to do that, really straightforward, let's add a new pin on our sequence node, drag down and add a reroute node. And we'll add a new local variable, and that will be called final score. Drag that on as a set node and hook that up. And now we just need to get our weighted priority score, our weighted recency score, and our weighted distance score, and add these 3 together. Add a new pin for a third add input. But we're not quite done yet. The last thing that we're going to do before calculating our final score is to multiply this score with our has investigated multiplier. So we'll add a multiply out of our return node here. We'll get our get perception scoring value function and select the has investigated multiplier. And out of the input here, I'm going to drag off and type select, and we'll select this one here under the utilities heading. And for our index wildcard, we want to use the has investigated local variable that we set at the start of this function. So we'll plug that into the index here. If has investigated is true, we will multiply this score with the has investigated multiplier. If it is false, we will just multiply it by 1, which will return exactly the same score as what this output provides. So we'll hook this up to our final score and that is our final score calculated. Just comment out this, calculate final score if MPC has already investigated the stimulus, apply the has investigated multiplier to reduce score. Compile. So we're basically done with this function. All that's really left to do now is to add in some debugging so we can actually print all this information so that we can see all the results from our scoring and make sure that there's no issues anywhere. Now to do that, I'm going to create a special function to print these values to the screen. But before we do that, I'm going to go all the way back up to our handle sound stimulus function. And right at the very start, when we first enter the handle sound stimulus function, I'm going to add a few variables to this input here. Firstly, I'm going to add 2 Boolean inputs. So I'll add 2 Booleans. I'll call the first Boolean print scores to screen. Second Boolean, I'll call print scores to log. And that will be the output log down here. The third input will be of type float, and I'll call this print duration. And the final input will be of type linear color, and it's this one here, linear color, and I'll call this print color. Now we need to promote each of these to a variable. We want to make sure that they're not local variables, because if we print these to local variables, we won't be able to use them in other functions. So make sure that you promote to variable, and we'll do that for each of these. And just hook up our execution again. Compile and save. So now if we go all the way back up to our event graph, you'll notice that our handle sound stimulus now has these inputs here that we can check at the top of the function as needed. And I might actually change the default color of this. So if we select the input node and we expand out the print color options here, the default value is currently black. I'm going to change it to white. And for print duration, I might change the default value to a value of 2 seconds. Cool. So now let's go back to our get score for sound stimulus function. Right at the end here, after our final score, we're going to create a new special function to print all the values to our screen or our log. So I will create a new function, and this will be called print debug sound scores. For category, I'm going to create a new category. I'll call this development. Now, if we just go back up for a second and drag this function onto the graph here, something we're going to do as well is we're going to mark this function as development only. And what that means is that this function will only run if you're playing the game in editor or you've packaged a development build. So if we mark this as a development only function, you can keep the actual function in the game. And if you package a shipping version of the game, this function won't run at all. Now to do that, we have to go to our editor preferences. So if we go up to edit and select editor preferences, what we have to do is we have to assign a keyboard shortcut to be able to enable development mode. So under general and then under keyboard shortcuts, what we're looking for is if we go ahead up here and type enable node, the one we're looking for here is enable nodes development only. Now what you can do is you can assign a keyboard shortcut here. I've gone ahead and assigned Control-Alt-D, but to assign a new one, all you have to do is select this, and I'm just going to type Control-Alt-D again, and then that way we can enable a development mode on functions using the command Control-Alt-D. So I'll go ahead and exit out of that and go back to our event graph. I'll select the function and press Control-Alt-D. And now you'll notice that it's been marked as development only. Now we need to add in a lot of input nodes here because we need to feed in the values from a lot of our local variables. And we can't use these local variables inside this function because these variables only exist inside the get score for sound stimulus function. So we're going to have to go ahead and add some inputs for each of these. I'm going to add 9 inputs. Go ahead and add the first input. This will be of type Boolean, and this will be called is primary. Second input will be of type integer, and this will be stimulus ID. The next input will be of type float, and this will be raw priority score. The remaining 6 inputs will all be floats as well. So I'll go ahead and add 1, 2, 3, 4, 5, 6 more floats. I'll name this one raw recency score. Next one will be raw distance score, and then weighted priority score, weighted recency score, weighted distance score, and then finally final score. And now we just need to hook up our local variables to each of these inputs. Now for is primary, this isn't actually a local variable. We're actually going to be using the output from our input node here. And to do that, we can just right click and type in is primary, and under variable, select that one. And because it's got the little picture of the F here, that means it's an input from the function. So we'll hook that up to is primary. Next, we'll get our local variables. So stimulus ID first, raw priority score, raw recency score, raw distance, and weighted priority score, weighted recency score, and weighted distance, and then finally our final score. Great. So now let's go inside this function here. Now, a little bit of a quirk with it when it comes to Unreal is that the print string node, let's just bring this print string node onto the screen. This is only going to print something on one line of text. And we don't want all of this information to be printed out on one line. But rather than doing each of these on their own print string functions, we're going to be doing a for loop. But an interesting quirk about Unreal is that if we print to the screen, it's going to be in the reverse order than it would be if it was printed to our log. So if I just show you my example project here, if we're going to be printing the scores to the screen, we'll be using a reverse for each loop. Whereas if we print to the log, we'll just be using the for each loop. And that way they'll be showing up in the order that we specify for each. Okay, so let's go ahead and do that. So I'll expand this out, and for this one, for this print string node, we're going to use this as our print to screen. So I'm going to have print to log checked off. For the text color, we want to use the print color variable that we created. And for duration, we want to use the print duration variable that we created. And now what we need to do is we need to add in a reverse for each loop and hook that up like so. And then if we hook up the array element into in string, this will change the array element to a string as well as the array input. So we're going to be making an array of strings. Oh, and a fun fact, just in case you didn't know, but a string variable is itself an array, and it's an array of characters. Just a bit of trivia there if you weren't aware. So to create this array, we're going to drag off this array input and type make, so we can make an array. Basically each array element that we add here is going to be a separate line of text. It's a bit of a hassle to do in blueprints, but this is a blueprint only project, so this is how we'll do it for now. For our array item 0, what I'm going to do is I'm actually just going to type in a line of dashes here. It's just going to be easier to visually separate the chunks of log if we use a separator. So we'll add a new pin for item 1, and in array element 1, we want to mention whether the sound stimulus is the primary sound stimulus or the competing. And we also want to add the ID for the sound stimulus as well. So what we'll do here is we need to append some information. So out of array element 1, we will append. And append just means adding two things together on the same line of string. In A, we want to say whether it's the competing sound stimulus or the primary sound stimulus. So we need to actually select something to go into A. So I'll drag out of A and type select and just grab the select under struct. For our wildcard, we'll use the is primary input. So I'll just right click and type get is primary, and then under variables, hook that up to the wildcard. If is primary is true, we will write the text primary sound stimulus, and if it is false, competing sound stimulus. And then next in our append for B, we'll do space, hyphen space, and then ID colon, and then another space. And then we'll add a new pin, and in C, we'll add the actual stimulus ID. Now we do have our stimulus ID count integer. Now there is a chance that if you have multiple aliens in the environment, and we will get to handling multiple aliens, but there is a chance that if you have multiple aliens in the environment, you'll have sound stimuli that will be the same ID count. So we need a way to differentiate two sound stimulus IDs from different aliens. So what we'll actually do is we will append some information. So let's type append in C. And for A, we're actually going to feed in the specific world reference to that particular alien character. So we'll get our alien character ref, and then from there, get object name, and then feed that into A. Now what get object name actually does is it doesn't just return the class of the alien character. It will also return the specific instance of that class in the environment with a unique name. So this is a way that we can differentiate the stimulus ID. In B, we'll do colon and then space, then add another pin, and then hook our stimulus ID count up to C. So I know this might be a little bit head scratching at first, but essentially what this first array element is going to read, for example, is primary sound stimulus, and then ID equals alien character reference ID plus the stimulus ID count. So it's all going to make sense eventually, but it might just be a bit of a head scratcher at the moment. That's fine. Now, out of our make array node, we'll add the next line. And what I'm going to do here is I'm going to drag out a 2 and again write append. And in A, I'll write raw priority score space equals and then space. And then in B, we'll get our raw priority score output here by right clicking and get raw priority score, and then hook that up like so. And we'll be repeating this same exercise again for the rest of those variables. So we need to create another 6 pins here. So 1, 2, 3, 4, 5, 6. And I'm going to copy this append node another 6 times. So 1, 2, 3, 4, 5, 6. And I'll just change the text here. So rather than raw priority score, this one will be raw recency score. And we will get raw recency score, hook that up. Next will be raw distance score. We'll get the raw distance score. Next will be the weighted priority score. Next will be the weighted recency score. Then the weighted distance score. And then finally, the final score. Now we'll just get the final score onto the graph, but because our primary sound stimulus is getting the hysteresis bonus applied, we just need to treat this part a little bit differently. So what I'm going to do is I'm going to get is primary. So I'm going to drag out of B and I'm going to type select, but this time rather than selecting the select struct, I'm going to select the select string function. And I'm going to hook is primary into pick A. So if is primary is true, we will pick the A string. If is primary is false, the final score is simply the final score. But if is primary is true, we need to get the final score and then add, if we get our get perception scoring value and get the hysteresis value and add that to our final score, then out of the A input of our select string, I'll just add an append node and I'll hook this up to A. And then in B, I'll write space and then in brackets, hysteresis applied, and then close brackets. And then finally, we just need to make sure that all of these append nodes are hooked up to the make array. And I'm also just going to copy these dashes, add a new pin, and add the same amount of dashes at the end. So this will create a nice block of text that's more easily readable. So after we've done all of that, we'll go back to our input node here, and I'm going to add a sequence. Out of sequence 0, we want to only proceed to the reverse for each loop if print sound scores has been marked true. So we'll get our print scores to screen boolean and add in a branch, hook that up like so, and then out of the true pin, we hook up to our reverse for each loop. The last part will be whether or not we print to the log. So I'm going to drag out of the number 1 pin, add a reroute node down the bottom here. We'll get our print scores to log boolean, add in a branch, and then if true, rather than using the reverse for each loop, we'll just use the regular for each loop. And hook that up to true. And we don't need to create all the array items again. All we need to do is from the make array output here, we just plug this into the array input there, and we'll add in a print string function. And this time we won't be printing to the screen, so we'll uncheck that. We'll leave print to log checked. The text color and duration are not relevant because the text color won't change in the log. So we'll just hook up the loop body and the array element to in string, and that is this function done. And we'll be able to demonstrate how this works in just a moment. But lastly, to finish off our get score for sound stimulus function, we need to add in a return node after our print debug sound scores. So we'll add in a return, and we need to feed in our final score from our local variables. So we're almost ready for testing now. I'll go ahead and delete this extra return node I had up here. One thing that we haven't quite done yet is that we haven't actually added the hysteresis bonus to our primary sound stimulus. So for that, we need to go up a few layers. Where are we? So in our handles sound stimulus, where are we? Run sound stimulus decision tree. So in the get higher scoring stimulus function, this is where we need to add in the hysteresis bonus. So once we've got the stimulus score for our primary sound stimulus, we will add that to our hysteresis, and then that will then go into our greater than node. So if our primary sound stimulus plus our hysteresis bonus is greater than the stimulus score for our competing sound stimulus, then is A will be true and the primary sound stimulus will win. Great. So that is effectively everything in place for this function to work. So now let's go do some testing. Now, I have just done some testing and I realized that there is a bit of an issue here. We actually have two problems. The first problem is quite easy to solve. If we go to our AI controller, the AIC MPC alien, in our AI perception primary in the hearing config, in the last episode, we set our max age to 5 seconds. We want to get rid of this because we want the alien to retain sound events in memory from much longer ago. So I'm just going to set this to a value of 0 to eliminate the max age entirely for now. And we'll go to ahead and compile and save that. But the second issue is a little bit more pervasive, and I'll show you how I was able to actually find out what the issue was, but I'll go ahead and show you the issue that I was facing. So if I go behind one of the structures so the alien can't see me, and I press play, if I press the N key and wait for the streak window to close, and then press the N key again, you'll see that nothing is happening. And if we go ahead and look at our alien, it appears to be locked inside a wait state. Now, what's happening here is that in the state tree, it's reaching the wait state and it's failing to transition out of this. And what happens then is that because the transition has failed, it then triggers the tree stop event in our parent evaluator. So our evaluate perception evaluator derives from evaluator base class. And in that base class, when the event tree stop event fires, we basically unbind all of the AI perception component events from our custom events. So when this tree stop fires, we're no longer able to access any of the perception events from our perception components. So this is a real problem. But I'll show you what's actually happening here. If we go to our state tree, I'll show you how I was able to work out what was going on here. Because if we go up to Window and then select Debugger, we'll get access to the state tree debugger. Now, this is extremely useful for debugging your state trees. It probably deserves its own video. I'm going to go ahead and press the record button, and you can start a play in editor session from clicking this pause button. But that's going to open up on a separate monitor for me. So I'm just going to play the session normally, go behind one of the structures here and then press play, and we'll reproduce our event. So I'll press the N key to trigger a noise event, wait for our streak window to close, and then press N again. You'll see that nothing's happening, and you'll see that our alien is locked in its idle state. I'm going to exit out of the Pi session, go back to our state tree, and you'll see here that we've recorded a debugging session of everything that happened on a timeline in our state tree. And you can see how the information updates here as we scrub through the timeline. I'm going to go to the very end of the timeline because this is where the information is. You'll see this exclamation point here. It says could not trigger completion transition, jump back to root state. And if we have a look here, you'll see what's going on here. It's trying to see which state it can transition to by checking against all of the conditions that we assigned. For idle state, there's only one condition and that failed. For entering the search state, only one of those conditions succeeded, the other one failed. What failed for the search condition, it says that the condition to not include receive stimulus failed. So it has recorded a receive stimulus gameplay tag. And for the attack state, what failed is that motivation was a mismatch. And this is where we can really fix up the issue and create a state that is more appropriate to transition into. So I'm going to exit out of the debugger and I'm going to create a new state. I'll call this investigate, and I'll give this a color theme of yellow, which I've already assigned here. And I'll just select the investigate theme color and I'll drag this up in between search and attack, and you want to make sure that you don't child this accidentally to the search state. You want to have it as a sibling of the search and the attack state. Now we need to create a new motivation gameplay tag. So I'm going to go to the content drawer, and in our blueprints AI alien data tables folder, we'll open up DT alien motivation, and I've created a new gameplay tag here of alien.motivation.investigate. So go ahead and add a new gameplay tag of alien.motivation.investigate, save that, and we'll go back to our state tree. And for our enter condition, we'll add a new enter condition of compare gameplay tags. For our left tag, we will bind this to our motivation parameter. For our right tag, we will select alien motivation investigate. We will leave exact match unchecked because we will have subcategories of the investigate gameplay tag. Next, what we'll do is we'll just add a task to this state. So if we go to tasks and add a task, we'll just add a delay task, and we'll just simply run this delay task forever. So when we enter the investigate state, we'll just stay there, and that's fine for now. Now we need to create a transition rule so we can transition from the search state into the investigate state. So we'll select the search selector branch, and for transitions, we'll add a new transition, and the trigger will be on tick, and we will transition to the investigate state. And we need to assign a condition. So when compare gameplay tags, left tag will bind to our motivation parameter, and right tag will assign to alien motivation investigate. Save that. Now we're not quite done yet because we need to go back to our evaluator, and we need to implement this gameplay tag into our handle sound stimulus function. So we'll go back inside there, and what I'm going to do is I'm going to change our run sound stimulus decision tree slightly. So if we'll go back into there, because if we go to this section here where we're adding the hunt motivation, and now this is in section 6 where we increment the streak count, I'm going to go ahead and highlight this and press Control X to cut. I'm going to go back up a level, and I'm just going to paste this in the event graph for a moment. I'll go back into the sound decision tree. I'll delete this print string node for now and just hook this up like so. And we're going to add a Boolean parameter to our return node. So we'll go ahead and add a Boolean output parameter, and we'll call this should hunt. And this is where we were triggering the hunt motivation. So this is the only time we need to check this Boolean output. So we'll go ahead and check it there, and every other instance of this return node will be false. So we'll go ahead and compile that and save, and then go back up a level. And now I'm just going to disconnect this execution and move this out a little bit. And rather than setting the hunt motivation here, I'm just going to delete this, and then out of the value input, I'm going to drag off and type in select. We'll select the select utility, and then for our index wildcard, we will plug in the should hunt Boolean output. And if should hunt is true, we will set the motivation to alien motivation hunt. If should hunt is false, we will set the motivation to alien motivation investigate, and hook up the execution. And then finally reattach the suspicious object location. Go ahead and compile and save that. Now let's give it a test to see if it's working. Go behind a structure so the alien can't see us. We'll press play. Press the N key, wait for our streak window to close, and then press the N key again. And now you'll see that our stimulus scores are being printed to the screen. It doesn't stay there for very long. I might increase the duration, but I'll just escape out of the Pi session because we should have also printed that information to our log. If we scroll all the way down the bottom here, here we go here. So you'll see that in both instances, no valid tag was found for get stimulus priority. So this is something that we need to set for where we're calling our noise event in the environment. But let's just have a look at what's actually been reported in this log here. So you'll see that competing sound stimulus ID equals, and this is the unique identifier for the instance of the alien class that's in our world. And then the ID count is 2, which is actually incorrect because they're both reporting 2. That should not be the case. And I think I know why. If we go back to our print debug sound scores. Yeah, so I've made a mistake here. So what I'm printing to the screen here is the stimulus ID count, and that is the member variable of the class. It's not actually the local variable that's been fed in through here. So if I right click and type in stimulus ID, we want to get this one here, which is the function input with the F above the variable. So if we plug that into there and delete the class variable, that should now work. I'm going to go ahead and press play, press the N key, press the N key again, and that is now fixed. We'll go back to our log. I'm just going to dock this to our screen here. Great, so now we have the scoring values for our primary sound stimulus and the scoring values for our competing sound stimulus. For each of these, the raw priority score was 0.3 because we have not actually assigned a tag to our noise event, so we'll do that on the next test. Let's see how they compared with the raw recency scores. So the primary sound stimulus occurred first. So the raw recency score for the primary sound stimulus is lower than the raw recency score for our competing sound stimulus because this one was heard earlier. Our raw distance scores are essentially the same because we didn't move the player character in between these sounds events. The weighted priority scores are each given a value of 0.06. The weighted recency scores are very similar. The competing stimulus scored higher because it was more recent. Weighted distance scores, again, the same. And our final scores, so we have a final score for our primary sound stimulus slightly higher because of the hysteresis bonus that has been applied. So the primary sound stimulus wins out of these two events, mainly because of the hysteresis bonus that was applied. But let's test to see if our tag converter function is working. Let's open up our player controller. Let's add in a flip-flop node. On the first noise event, let's report a footstep. We'll use the footstep tag, and just remember to spell this exactly the same as how you spelt the data table row. And for our second noise event, let's add in the player character as the instigator and the actor location as the noise location. And we'll change this tag to gunshot and we'll hook up the execution. So this noise event should score a higher priority score because gunshot is considered a high priority noise and footstep is considered a medium priority noise. So let's go ahead and test that now. Go ahead and press play. Press the N key, wait for our streak window to close, and then press the N key again. And we'll exit out. Okay, so for our primary sound stimulus, which was the footstep, we had a raw priority score of 0.6, which is correct. And for our competing sound stimulus, which was the gunshot, we had a priority score of 1.0, which was a higher priority score. And in this case, the competing sound stimulus actually won over the primary sound stimulus, even with the hysteresis bonus applied to the primary. Now let's do one more test. Let's test the distance score, and let's leave a longer duration in between sound events so that we can have a primary sound stimulus that is much older than the competing sound stimulus. So let's go ahead and press play again. I'll press the N key here and I will walk to a further away location. And I'll wait a little bit longer, and I'll press the N key again now. And then let's exit out of high and let's take a look. So again, the raw priority scores are the same as before, but this time the competing sound stimulus had a recency score of 1.0 and the primary sound stimulus had a recency score of 0.879. And as for the distance scores, the primary sound stimulus scored much higher than the competing sound stimulus, which only scored 0.19. And of course, because of the higher priority noise event that occurred, the competing sound stimulus still came out on top. So this is everything working. We've covered a lot in this video. It's been quite a long video, longer than usual. And we still haven't really implemented these noise events into an actual practical gameplay component now. So in the next video, we'll incorporate this system into some actual gameplay and finally round out our hearing perception sense. I hope you guys enjoyed the video. Please be sure to like the video and subscribe to the channel, and I will see you in the next lesson.